All right, continuing in the series of physics topics and formulas, here's work and energy and conservation of energy. Remembering that energy is the capacity to do work, therein lies the work energy principle. The work input to a system is equal to the change in energy. So work is equal to force times distance. Important that force and distance must be parallel or moving in the same direction in order for work to be performed. Work won't happen if force and distance are perpendicular. That's torque, and we'll get to that later. Kinetic energy is equal to 1/2 mv squared. Gravitational potential energy is equal to mgh. So if we look at a situation where we have a person dropping an object off of a building, gravitational potential energy at the top, mgh. If we're going to let m be 10, g be 10, and h be 10, gravitational potential energy at the top is equal to 1,000 joules. So as an object falls, it gathers kinetic energy. So at the middle, the height equals 5, then the gravitational potential energy equals 10 times 10 times 5, or 500 joules. The kinetic energy makes up the rest, the other 500 joules. So the total energy is conserved. So the total energy that it had at the beginning of 1,000 is equal to 1,000 in the middle. Total energy conserved, GPE plus KE is always constant. And then the KE at the bottom is 1,000 joules, which is equal to 1/2 mv squared. So if we calculate just the velocity at the bottom, we would set the velocity or the kinetic energy at the bottom equal to the potential energy at the top. So mgh would equal 1/2 mv squared. The m's would cancel out. v squared would equal 2gh. So then v is square root of 2gh. Now, if in the case where we have a roller coaster, we've got, if no friction, total energy is conserved. So mgh at A is equal to kinetic energy at D, where the height is 0. So whatever the mgh at A would be, and it's assuming that it has no kinetic energy, give it a little shove, allow it to roll, that is, not a shove, but just allow it to roll, and now the kinetic energy at D would be equal to the potential energy that it started with. If there is friction present, then the work done by friction force times distance, is equal to the change in energy. So if it slows down, then the energy or the work is negative. All right, so in case where we have a spring pulled back and we have a ball on top, we're going to let go of this plunger and it's going to spring the ball up in the air. The question is, how high will the ball go? At this point right here, that's the point where the spring is in equilibrium. That's where the applied force stops. So that 1/2 kx squared is the elastic potential energy in the spring. If that is released, then it converts to kinetic energy up to this point, and then kinetic energy is depleted as gravitational potential energy is gained. So if we go through the process again, we've got stored energy in the spring. Once we release that elastic potential energy, 1/2 kx squared, it transfers into kinetic energy, which transfers into gravitational potential energy. So here we go with elastic potential energy, 1/2 kx squared. K is a spring constant, and Hooke's law says F equals kx. K is the stretch, F is the force, F is the force, K is the spring constant, X is the stretch. There we go. And so if we graph force over stretch, K then becomes the slope of the graph, and it's kind of in the same slope intercept form, y equals mx plus b, b being 0. So another revisit, if we have a kid jumping off of a 5-meter tall garage and jumps onto a trampoline, his gravitational potential energy at the top is equal to the kinetic energy at the surface. Reason that is because at this point he's making contact with the trampoline, which is slowing him down. That's all kinds of elastic potential energy at the bottom. So remember that the total is conserved or is constant. So mgh at the top would be equal to the elastic potential energy at the bottom of the trampoline. So another thing to just remember, rotational energy is coming up in another. So rotational kinetic energy is 1/2 I omega squared, and that we'll get to that when we talk about the total energy of a bowling ball. We talk about translational plus rotational. So the total energy is 1/2 mv squared, which is moving it along, and then 1/2 I omega squared, which is allowing it to roll. So we'll have more of that on a future video, but have a lot of fun with this one.